Very good.
Welcome, everybody. I'm Olof Mogren, and this is RISE Learning Machines Seminars. RISE is Sweden's public research institute with more than 3,000 people working on a wide array of topics. Specifically, the computer science department works on AI projects with applications in ecology, health, remote sensing, natural language processing, etc. And we organize these weekly Learning Machines seminars. This meeting will be recorded, and if anybody wants to be removed from this recording, just let us know. Be sure to check out our collection of amazing talks on our YouTube channel. Today, I have the honor to introduce Professor Klaus-Robert Müller from TU Berlin. He's also the director of Berlin Machine Learning Center and co-director of Berlin Big Data Center and Berlin Institute for the Foundations of Learning and Data, BIFOLD. Professor Müller has a PhD from TU Karlsruhe, and he had a postdoc at GMD First Institute in Berlin. He's received numerous awards for his contributions to the field of machine learning, pattern recognition, and signal processing. He's also made many important contributions within nonlinear component analysis, optimization and learning algorithms for neural networks, kernel-based learning, and methods for interpreting and understanding deep neural networks. His research interests are within intelligent data analysis and machine learning in the sciences, including neuroscience, physics, and chemistry, and in industry. The topic today is machine learning and AI for the sciences towards understanding. And with that said, I will hand over the screen sharing and the floor to you, Professor Müller.
Can you see my slide?
Yes.
Wonderful. Yeah. Thank you very much for having me. And it's always a nice thing to give presentations across the globe. The nicest thing about this is actually to get to know the people, which is a bit difficult in the online case. So I apologize that we have it like that. Yeah, I'm running BIFOLD, which is one of the 5 national AI centers in Germany, together with my colleague Volker Marke. To give you a bit of an understanding, we get something like 22 million per year, which is not only for Volker and me, but also for a lot of professors that we are hiring, and for a lot of postdocs and PhD students, and computers and all that. So it's a very luxurious funding, in particular, because we are having that on a permanent basis, unless, of course, we mess up. So I think, having said this also gives a unique opportunity to host people visiting us at all levels. So we are doing this with different places in the world, for shorter or longer term, or even for people who are curious to live in Berlin for a while. So this was a bit of a self-advertisement. Also, we are one LS node. I will today speak a bit on machine learning for quantum chemistry, mainly because I was trying to focus myself somehow, but I also talk interleaved in this about explainable AI. So the 2 main things that I will talk about is predicting across chemical compound space and also molecular dynamics. And the recurring topic will be the gaining insight part. I see someone with a tie Torstein, that's so nice to see you. So just happened to be around the first couple of pictures. So I'm sorry for interrupting my talk. It's good to see old friends. So let me come to machine learning for chemical compound space, and I would like to start a bit with a story of how this came about. I'm telling this story because a lot of people, in particular younger ones, they feel that science can be planned somehow, and and I think it cannot be true. It cannot be like that. So science is a very dynamical thing, and it's full of serendipity. So here's my serendipity. I got an invitation by IPAM, which is the Institute for Pure and Applied Mathematics at UCLA. They run long and short-term programs, and I was invited to a long-term program, which is 3 months. So I was up for a sabbatical, so I got permission from my family to go to California, of course, only if they could come. So this was a good thing. And what I didn't do is really read this invitation carefully, because I thought there's nothing wrong with spending 3 months in California. But apart from that, I learned a couple of things when I got there. So first of all, LA is a wonderful place, and IPAM and at UCLA is really great. The reason for this is because if you usually do a sabbatical, then you come to some place where everybody except you is extremely busy. And so it's very hard to get people's time and attention and to install collaborations because people are busy. They need to do their job. It's different in IPAM. So they invite something like 15 professors from all over the place, and they're allowed to bring their students. Not all of them, of course, but some PhD students, some postdocs. So it's in the end, it's a group of 30, 40 people, and they are basically in one building with a lot of space to communicate and a lot of whiteboards. So since everybody is on the sabbatical, one is under the obligation to actually do something. And so what was the program about? It was about quantum chemistry. And I realized this because there was a tutorial week, and people talked about quantum mechanics and chemistry, and they also talked about DFT, which I only knew under the name of discrete Fourier transform, but it turns out that when the chemist talks about DFT, it's density functional theory, which got some Nobel Prizes. So the idea for the chemists is basically to solve this nicely, beautifully looking equation, which is suspiciously innocent, but it's actually quite a bitch. So, if you want to solve the Schrödinger equation, if you would do this naively, then the system size would be 10 to the 60 or so, which no computer on this planet can do. So only approximate solution of the Schrödinger equation are doable. Practically, why would you want to solve the Schrödinger equation? Because it describes the foundations of quantum properties of matter, molecules, materials, everything. So when we had this tutorial week, everybody was trying to explain in a gentle way, because there were several communities involved. I was the only machine learning dude. So, we explained things to each other, and I realized that I was actually trained in theoretical physics, and I actually knew what quantum mechanics was, having done some strings back in the days. So this sounded somewhat familiar, and what the chemists said is, in order to solve the Schrödinger equation, you approximate it. And this means that you try to make an approximation to ultimately get energies and polarizations and whatever you want to know about the chemical system. This is really tedious. It takes a lot of compute, and it takes practically almost as much compute as the climate people would take in terms of supercomputing time. Everything else is almost of the order of zero measure. So after a while of listening to everything, I thought, well, how about being a bit heretic? How about, instead of doing this approximation, I suggested to treat this whole problem as a stochastic problem and to use a machine learning model to predict the outcome of the Schrödinger equation, which is something not really that people would like to actually do normally in math, because you solve your equation, you don't predict the outcome of an equation. This is a no-no. And people, mathematicians, physicists, and chemists, they were not really agreeing on how to kill me, but somehow they didn't. In the end, I suggested this, and a couple of people actually went along. So of course, the young people wanted to try this. So we put in everything into a machine learning method that you would typically put into this approximative solution. And then the question for machine learners is always, how can we compare things? I mean, it's all about comparing things, the whole machine learning world. And so how do you compare molecules? Assume that you know the quantum property of one molecule, and then you say, well, maybe molecules that are not far from this molecule, they have similar properties. And so how about measuring that similarity? So for this, we have to represent a molecule in terms of, a vector or a matrix or a tensor or something. And here is a molecule, and basically we have the nuclear charges, the Zi, and the R is the respective 3D coordinate of this, in case, first atom. So we basically said, well, how about, representing the molecule in terms of a matrix, where on the off diagonal, we find the Coulomb force between the ith and the jth atom. And on the diagonal, we have this notorious Zi to 2.4 that only Anatol von Lilienfeld, one of our co-authors, can explain in a very coherent and nice way. So practically, the Coulomb force is something important for a molecule. And so basically everything in how to represent it is a matrix. And then we know how to compare matrices. If we have one matrix representing one molecule and another matrix representing the other, then we can take the Frobenius norm, and then we see the distance, and then so we can go beyond that. And I insisted in trying something that is called a kernel ridge regression, which is machine learning 101, where you have a kernel in which you put in the distance function, and you have some scale, and then you put it into the kernel ridge regression equation. And the only thing that you need to learn is these alphas and perhaps the B. So because then, given this kernel matrix and given the training set with all the molecules and matrices there, you can compute the distance in terms of this kernel function of an unseen molecule to all the rest of the data set. You weight it, and that's it. Then you get a prediction. It's a very simple thing. So of course, how do you learn this? It's basically you learn it in the way that you learn in kernel-ridge regression, which is solving this minimization problem, and this is closed form solvable very easily, right? So that's very simple. And we have a bit of a regularizer here. So the interesting thing, and this is why I would talk about it, is unexpectedly for many people, it actually worked. So we could, generate, we had the Max Planck supercomputer run for about 8,000 structures. We took 1,000 to learn our kernel-ridge regression model, and then we could out of sample measure how good we were in our prediction. Now, with that, I think it's fair to say that in the beginning, our results were not so convincing. This was 10 kcal per mole. If you would take a mean predictor over the training set, then this would be like 350 kcal per mole. So it's a bit better than the mean predictor already. So it's also much better than a linear predictor. But as soon as we started to do neural nets and other things, we were essentially at what is called a chemical accuracy, which is below 1 kcal per mole. So the interesting thing here is, and I should say that these quantum chemical computations, they are very compute intensive. I mentioned this already, but for a small molecule, this would take something like 3 to 5 hours, right? For one sample point. For material, it would take like 3 to 5 months, depending on the complexity of the material. So in our case, the prediction with the kernel-ridge regression model takes a fraction of a millisecond. And given that we are, below chemical accuracy, this is something to write home, because we can basically be 30 or 40 million faster out of sample, right? Of course, we need to know when the method fails and things like that. And there's many papers on this. So this was we started with the Coulomb representation, and for a while people thought about new representations for molecules, for materials, for anything on the planet, and that's it. And then we realized, yeah, but there's stuff beyond the kernel world. It's hard to realize, but it is true. And there's deep learning. And the nice thing about deep learning or neural nets is that you don't have to fix the scale beforehand, scaling under which you compare things, but you can learn it. And you can also use the architecture to include some of the prior knowledge inside. So now we are, I will be talking a bit on DTNN and deep tensor neural network, SNET and others, which are the models of that time. So one first thing that we did in 2017 was the tensor neural network framework. And the idea was to say, how are people learning language? So at that time, people would look at, embeddings at word2vec. So they would look at a word in its language context. So we were inspired by that and said, well, how about taking an atom in its chemical context? And how about learning how this chemical context, how this materializes, given a certain data set. Okay, so the way we were thinking about this is basically first to embed the atom times, so that's so to say the zeroth iteration. Then we would add interactions between the different atom types, and then we would predict atom-wise the contribution. Okay, and then of course we could say, well, let's be a bit more interesting and not only consider the word, by itself, but also, so to say, let's consider the bonds, right, as the next thing, or let's consider larger context. And then basically we could, take into account the graph interactions, and we could learn that. And of course, you can do this many times, right? So this way, you basically not only you can extract from a data set how this embedding into a chemical environment, how this actually is performed. And the architecture is this one here. Oh no, I'm not yet there, but I will show you the architecture in a second. It's not really important, but it's just a neural network architecture that takes into account these things and that can be learned and trained efficiently. The next thing that we thought about was, how about going towards the ConvNet architectures from the tensor neural network, which is a bit more bulky, let's say. The ConvNet is something that everybody knows very well, and it has this discrete filter that you learn in order to understand what are the interactions, typically in computer vision, at certain scales. And so the interesting thing about this discrete filter is that, it's discrete. So if we apply it to a molecule, then if the molecule dances a bit, it just moves a bit its coordinates, then the filter response, because it is discrete, may yield the same result. Quantum mechanically, however, if you change some structure in the 3D structure in the molecule, the energy or any other quantum properties may change big time. Okay? So a discrete filter will give you the same result, although quantum mechanically things have changed drastically. So this is no good. So we thought, how about inventing some discrete continuous filter ConvNet? And it turned out that there were no continuous filter ConvNets. So we thought, okay, how about getting continuous filters into a ConvNet architecture and then applying it to this quantum chemistry? And we did this, and everything worked out very well, and we got amazing results. Okay. So the interesting thing is that basically we have a completely novel machine learning model from the physical question that we've asked. So the physics tells us discrete filters are no good for molecular dynamics. So we needed to find a new algorithm, which is continuous filters. And then all of a sudden, this contributed to machine learning literature. And, since at some point, people realized that sometimes not only in molecular dynamics, but also in other contexts, it's quite handy to have a continuous filter. Some new architectural element was born. Of course, more recently, we have also played with transformers and equivariant models and so on and so forth. I spare you these details. Now, if I think about it, one thing that was worrying me at that time was that we have our model, our machine learning model, and this machine learning model is making some predictions. But the question is, are we actually knowing whether it makes silly predictions or whether it's capturing some artifacts in the data or whether it's actually learning chemistry? Okay, so let me just for the moment talk about a field which is called explainable AI that I've been pushing forward since, I think now 13 years. So here's the question. And now not in the chemical language, but in a more computer vision language. So assume that you have trained your model. Your model is done, it's fixed, it's the best model that you can think of. Now the model makes some prediction. For example, it gets this input image. It's the first time that it sees that, and it predicts. And here, because this is a rooster and this is a good model, it says it's the rooster class. Now, you may ask, why is this particular model that is fixed and trained, why is it thinking that this is a rooster? What's so roosterish about this in the light of this neural net? And this actually is an interesting mathematical problem, because this neural net is a very nonlinear beast. So we can invert linear functions easily, but nonlinear functions, it's a bit difficult, right? And so this part was not solved. And then in 2015, our paper finally got published, after many people telling us that this was an irrelevant problem, that to explain things. But anyway, so we solved the math problem, and then we can put, so to say, the nonlinear model upside down, and then say in terms of the input features, what are the most important input features? And here's, the red dots. That's, so to say, speaking for the decision that this is a rooster. Green is neutral and blue speaks against. So you can see that these red dots are exactly the positions where the rooster has a comb on top of the head. So the model thinks that this is a rooster because of its comb. And so this is quite nice. And just to remind you, trying to understand what models do is an old thing, right? Control people have been doing this forever their life. It's called sensitivity analysis. Now, the algorithm that we're using and proposing is different than sensitivity analysis, and that's important to note. And that's one thing. The other thing is, quite often people say, they speak about feature selection. This is like an own topic in machine learning. And the question in feature selection is, which of the features over the whole data set, over the whole class that we have, which are the most important ones for decision making? And here it's a different question. We're asking for one data set, one data point, right? And of course, it depends on your perspective, right? Whether you ask the ensemble question or whether you ask the individual question. So if you say you're a patient, right, then you would like to know why you have a certain disease. You personally, it's your data. And so that's this one perspective that we are adopting here. It's this single data point explanations. Whereas the FDA takes another perspective. The FDA asks, in this general disease setting, what are the most important aspects and features that make this disease, right? Now, as a patient, you couldn't care less about the other ill people. You want to know about your case. So just to know the difference of these questions. Both are valid questions, depending on your perspective. Okay, so the algorithm that we conceived was called layer-wise relevance propagation, and it can be applied to neural networks, to kernels, and to anything. And you can see that coffee is considered coffee because of the crema. Cats are cattish because of their mustache and the fluffy bit. And depending on the cats and the background, the explanations are different. So the idea in layer-wise relevance propagation from the theoretical perspective is you would like to have this decision so you have the classifier surface in high-dimensional space, and you would like to, in a sense, explain how it is, right? How it's located, and when it's curved, and so on and so forth. So you would like to know, and in a way, you could perfectly describe this function if you would take a Taylor expansion. Now, the Taylor expansion around one point. So that is a bit of a problem, because if you do a Taylor expansion around one point, then you need higher order points, because this is a complex function. So you have higher order terms all the time. So what layer-wise relevance propagation does is it does a linear expansion around different root points. And the nice thing is that you can prove that this is equivalent to an expansion around one root point of taking into account all the higher order terms. Okay, so layer-wise relevance propagation needs to be carefully chosen, depending on what kind of layers you have. If you have a max pooling layer, if you have a conv layer, if you have attention, and so on and so forth. So this needs to be adapted to the problem in terms of this Taylor decomposition theory. So it's very important, if you use these kind of methods, that you actually do the right thing. Otherwise, you shouldn't complain. So this has been applied to all sorts of different models, LSTMs, transformers, graph neural networks, anything on the world that is existing, and also most recently to unsupervised learning. That has been applied to all sorts of different data, neuroscience, but also in medicine, cancer, anything that you want. So now we have a technique which is called layer-wise relevance propagation that allows us to actually understand how decision-making was done. Okay, so far so good. Now let's take a bit of a step back. So this is what we teach to our students. A machine learning model is a beast that can has some data that it learns from, but the idea is not to learn the data by heart, but rather to predict such that it generalizes on unseen data. So that's the thing that we teach our students, and that's of course correct. But the question is that really all that we need to know, the number of the generalization error? And I would try to convince you that there's more. Okay, here's a nice data set. It's from the computer vision community. It's Pascal BOC. It served the community for 10 years. And the idea there is that you have some models. Here in this case, it's a deep net and Fisher. And you have the exercises to distinguish between different classes. And you can see that some things can be, recognized well. And sometimes one model is better than the other. And so when you write a computer vision paper, then essentially you have all these tables inside where you show the generalization error. Now let's look at one part of this table and let's see, okay, both models are actually very good in recognizing horses. And let's take one data point that we put into both models, and that's the data point. It's clearly a horse, and both models say it's a horse. And clearly you could not see a statistical difference between the generalization error of both models, right? So now you can look at how the models solve the problem, because you have explainable AI, you have an LRP heat map that shows everything. So the deep neural network basically captures the object. It looks at the horse's nose, at the horse's butt, the rider, and so on. So that's good. Then Fisher actually looks at all sorts of things, also the horse's butt, but also, most importantly, to the lower left corner of this image, right? And I can really see a horse there, right? Except if you read very closely, you see a copyright tag in the lower left corner that was more or less undetected in this Pascal VOC thing, which was specific to the horse class. So about 50% of the images had this copyright tag. And I read it to you. It's called Lothar Lenz Pferdefotoarchiv.de. So when I showed this picture to my wife, and I said, well, this model is doing a lot of nonsense, right? Then she said, well, no, it's actually able to read, no? And so practically what the model does, it cheats, right? It doesn't really classify this as a horse because of the concept, but it classifies this because of an artifact. Now, for horses, this may be a bit funny, right? But if you think about a medical diagnosis, then you rather want to be diagnosed by this kind of model, of course, not trained on horses, but on medical data, and then on this data. So practically what you see is you can't always read off from the generalization error whether a model is just doing some nonsense or not. So, and I will just show you another horse, and this is why we named this effect after. The horse's name is called Hans. So the horse was a horse in Berlin in 1900 something, and the horse was super famous because this master of the horse trained the horse to do math. So on this table you see different math exercises like 3 + 2, and so when the master would present one of these squares with a math exercise, then the horse would take its hoof and tap at the wooden block the respective number of times. 3 + 2, it would tap 5 times. So the horse would always get it right. And the journalists are very excited. Every journalist on the planet was saying horses can do math. It was a total sensation. And so then after a while, people of reason started to also think about this problem. And they also realized that horses are actually very, very sensitive animals. And what the horse actually did was it was reading its master. And they exchanged the master by some random other human that the horse didn't know, but still the horse always got the math right because it was reading the human. So in the end, horses cannot do math, but this horse was using a very simple and efficient strategy to always solve the problem correctly. And this is why people call this horse Clever Hans. So when we look at this, then we see that this particular model is of the type Clever Hans, and this one isn't, right? And so I think it's very important to understand this and to be careful that we analyze our models carefully so that we know that these models are doing the right thing for the right reason, right? So having said this, we can now continue. And this, by the way, the field is called explainable AI, the books, and this is the Unmasking Clever Hans Predictors paper that was coming up with this idea. Now coming back to chemistry. So I said we have a model that is super efficient, can predict 30 million times faster than you know, a quantum ab initio calculation, and it learns from data and it learns about an atom in its chemical environment, and that's the one part of the DTN, and that's repeated several times in several layers. So now you can ask, what did the model learn? And you can so to say query the model about the chemical potential that it thinks it has at some point near a molecule that you are looking at. And the chemical potential is in quotes. So assume that you are a hydrogen, then you could, you know, ask the model where, you know, where should I bind? And basically it says, well, in the middle, which is also not really a reasonable thing. But if you were a carbon, you know, you can also see what the chemical potential would be. And then you can look at many different molecules, and you can show this to chemists, and they're totally happy because that makes a lot of sense chemically. And you can also apply this to materials, and you can get very interesting insights. So one of the insights, and I would like to come to that point and emphasize it, is so quite often in machine learning, we are taking some data sets, then we are training a model, and then we're happy that the models predict well, and that's it. So, but the interesting thing is that these models that we have trained, you know, we can analyze them, can explain how they solve the problem, and we may actually find something that we didn't know before. And in this particular model, we have some, I mean, so there's the chemical concept of aromaticity. So you can study, you know, what the energy of an aromatic ring in a certain compound is. So it's not full molecule, but it's part of the molecule that contains the aromatic ring. And you know, the model actually learns some own definition of that concept, which is interesting and different from what one has otherwise, but very useful. So that is something that is never been explicitly in the data because you only know the energy of all the large compounds, but we don't know the energy of fractions. So this is just one example, and if you are not a chemist, you may not be very excited about it, but this is like something where you can definitely get some insights that you didn't have before. Okay, so there is something which is which I may spend a bit on. Now there's so chemical compound space. So I'm not sure whether you are aware of this, but if you think about all the small molecules, the combinatorics is amazing. So there's more small molecules than atoms of this universe. So the interesting thing is that these small compounds, they are quite useful. Some of them are aspirin and others are other drugs, and they're useful for all sorts of things. But what chemistry lacks is a map of this chemical compound space. And if you think why, it's clear, because you know it's just too costly. For every molecule you would spend hours of compute. Now we are spending fractions of a millisecond, but still the space is vast. But we can start mapping out the space and the properties of this space. And this is a quest that I think is a very useful one, because you know, people have been orienting themselves on this planet by making maps of the stars and orienting themselves in navigation. So I think this metaphor is showing very well that you could actually start a systematic way of navigating chemical compound space and searching for particular properties, or searching even for the boundaries of chemical space. So I don't actually know how much time I have, but I feel that probably I've taken up my time. And I would, before I skip through all my slides, I can just make some final remarks, which are just hopefully a bit enjoyable for you. And so I would like to talk a bit about differential equations, and in the particular set of differential equations. So this is not Schrödinger anymore, but it's a very profound one, which has to do with a differential equation that governs the trajectory of stones in curling traveling across ice, right? So it's remarkable that people have spent quite some effort in making some very sophisticated differential equations that over 3 or 4 pages that show how a stone which is having a curl goes across an ice surface with little pebbles on it for 40 meters or so. And so our idea was to say, how about building a robot that is able to throw curling stones, that we can teach how to throw these stones and how to play in a strategically meaningful way. So in a sense, curling is sometimes also called go on ice. It has a continuous space. It is high non-stationarity and is highly uncertain. So if you want to read about this, you can look at our Science Robotic paper. But the interesting thing here was that if you would just take a differential equation and throw a stone in a simulator that uses these complicated differential equations, and you give a certain curl, you give a certain push, then basically you will be, in simulation, you will hit the target. But if you do this in practice, not because the robot is lousy, but just because everything is real, you will be on average 3 meters off your target point. So we used a neural net to compensate for that. And then we got a bit interested to play this against humans. So you can hopefully see that now. There's actually hundreds of hours of footage available. And here's now the idea. So the robot first looks at where the stones are and measures where they are. And then the strategic engine is basically saying we should do a draw. There's 17 or 18 different ways of throwing a stone with a curl left and a curl right. And the robot pushes the stone and releases it at the hog line. And then basically the stone travels. And that's me. By the way, you can see me standing on the side of this. This was the first public demo. And we played against the Korean high school team, the best high school team available. So now the human is throwing the stone and giving some curl to the stone. And they are really good. So we played a lot of these games. But we didn't only play against the Korean high school team, but we also played against the wheelchair team, national wheelchair team, the women's team, the Olympic team. And so in the end, we are, I think if we count the sets, then we were one set in advance to everyone. But practically, it was a very even terrain. And so you can see now it releases the stone. Okay, so the stone travels, and yeah, so you can see it's a very complicated thing. If there are many stones thrown, then the ice changes quite heavily, and so this is quite precise. We have a similar precision than the human player, except that the robot is less nervous when it comes to a competition. So this was quite interesting for many reasons, because you would have to improve upon differential equations. You could do this in practice. You could do it really well, and you combine this with strategy. So this is just some example of many possible examples of this type of exercise. Okay, so I think we are really over time now. I showed the SNET and the DTN that learns to represent a chemical environment. The stuff that I went over too quickly that you could see it is that you can also put physical prior knowledge into the game, into the models, into the architectures. So you could get an understanding and insights. And interestingly, the AI applications and the science give you, in a sense, they force you to think differently and think anew. And so then you can also get new ML architectures. And so this is like a book that we had on machine learning meets quantum physics. And this is some explainability stuff. And there's the old tricks book that just I showed for nostalgic reasons. Okay, so yeah, please, I'm done, and thank you very much for your attention. And Olaf.
Thank you so much for this exciting talk. So please, everybody, bring out your questions, and let's discuss away. I would be very curious to know more about the continuous ComNet, continuous filter ComNet. But I suppose in the interest of time, it's perhaps too much to go into detail about how it works technically. But would you say, you mentioned that more recently people have worked with transformers and graph neural networks and things like that for chemical molecule representations. Would you say they compare reasonably well to each other, or what's sort of, which one is winning?
Yeah, I mean, I think honestly, I'm just to say that for the moment, I'm a bit annoyed by this SOTA hunting game. I think what we should go for is try to get new insights and understand more about chemistry and physics, or the respective AI application. But if you ask me about that, yes, the transformer, I mean, we had SpookyNet was the first transformer architecture used in the quantum chemistry context. Oliver Unke was the first author. It's in Nature Com from December 2021. But there's also, equivariant architectures. There's a recent submission that you also find online. These are, I think, state-of-the-art methods. They're a bit better than the SNET, but SNET is holding up very nice against the competitors, very robust in many ways. And again, in all these cases, we could look at the underlying strategy that the model takes and discover that the chemistry is right. So I think that's very important. If you are, maybe if we are in a less important environment, it may be not so important whether our model is doing the right thing. But in AI or in medicine, in the sciences, we really need to make sure that this is doing the right thing, because otherwise it's silly what we're doing, right? And again, I'm happy to even to discuss details about this, but the real, I mean, the trick in the continuous filter was that we have some basis, the filter basis in which we expand, and that is made in a continuous way. So it's not, so it's blazing fast and still continuous, right?
Interesting. And then, I mean, you mentioned the explainability things and the relevance propagation work. Is this sort of a tool to ensure that we learn causal relationships, or is it a tool to know that we'll learn the correlations that we're interested in?
I think, I mean, you're asking awfully difficult things. So causality is probably one of the hardest things that you can study. And so I think most of the applications that we have, people would be happy to just know associations, right? So I think this way I've been doing some work on causality, but I think that the point in using the explanation methods is to be able to debug the methods, to see flaws like the ones that I showed you. And interestingly, depending on whether you have supervised learning or unsupervised learning, the kind of flaws are different. So there's a paper that we will hopefully submit next week or so, which shows that in contrast to supervised learning, where you typically have flaws in the model because the data is flawed, in unsupervised model, you actually have the flaws because of the architecture. And that can be fixed, by the way. So, okay.
Interesting.
Mm-hmm. So you can debug the model, you can improve it, you can get insights, and there's a million things that you can do, right? But I think the point is that you need to have some handle to this nonlinear, machine that you have in your hands, so that you know that you're doing the right thing, and at least you're convinced that this is the case.
Absolutely, yes.
Mm-hmm. Okay.
So, more questions from the audience?
Yes. Actually, first, a big thank you to Klaus. A wonderful talk. Again.
Thank you.
Yeah, I have to thank you, Klaus, for doing so many great things to this field. It's really impressive. So I'm curious, since you talked about the relevance propagation, and you I say, okay, this is explaining, and of course explainability that's a really big question. Mm-hmm. Because you can show that, yes, we can see that these are the features, or these are the parts of the image that the model is looking at. But I would like to get your perspective on that. We're still quite far away from being able to explain what the model is doing. I mean, you can do it on sort of an individual pattern case. You can say, okay, so here's the image. This is what gave the biggest input. But to ask it, okay, so here's a group of horses, for instance. What is it that you define as a horse?
That's a very interesting question. So, and I say, I totally agree with you. I mean, this is not the end. It's a very active field, and there's abstractions to explanations. And there's a very nice paper by Wojtek Zamek's group, Archibald et al., which is the name is something concept-based something, and the question in a way is and that's already a meta question or an abstract question. So what is the explanation that is useful, right? And for which user? So I think a specialist, like a medical specialist, wants a particular kind of explanation that he's really particularly interested for the diagnosis in that moment, right? So as a physicist, if I may dream loudly, right, there's something which is called collective variables. So assume that you have a material and you would like to know the thermodynamic properties, then in principle, you could, of course, look at the atomic positions of every atom in this piece of material and then understand the thermodynamic properties like temperature and pressure, and from that, right? But somehow some very smart guy came about and found phonons, because phonons are exactly the collective variable that describes the whole thing, and it doesn't require all the single parts. So in a way, the question is, what are the collective variables that we are looking for in machine learning, if you want, right? And are explanation methods a good way of getting there? And I think no one has found the path yet, but it would be tremendously interesting if we could get there. And, you know, there's concept-based learning is one step, but there are different baby steps that people have been taking. And I think, for me, I think the most interesting point would be to piece them together with physics or with the medical questions, so that we can ask very fundamental questions in these disciplines. Okay.
Yeah, and I think that it's a special case. Well, okay, it's a very common special case where you have an image and you show it to an expert, and the expert agrees, yes, okay, I understand, these are important things.
Yes.
If you compare that to a case where I would like to have this totally automated model that actually runs and makes decisions, then you would really want to be able to say, okay, so what are the general concepts of this model that applies?
And I'm absolutely with you.
Yeah.
Yes.
So that was just my point, that I think that it's really interesting research. I really like what you've done. So thank you.
And I think that also, you know, for example, these algorithms scale linearly. So you can go over a very large data set and cluster the type of explanations that you get, or make some kind of statistics over it. So that is also possible. So I think, you know, there's a lot of interesting directions that we can go to, and causality is, of course, also, you know, a part of this, but I feel, you know, that's maybe a bit too tough at the moment. We need to understand things better before we tackle these things, perhaps.
Thank you.
Okay.
David? Oh, David?
Hello, thank you, Klaus, for a very interesting talk. I'm David from KDH, by the way. So I'm interested in these techniques like LRP and methodology you have for unmasking clever hands. If that is also applicable to more transformer technology, and also, you know, understanding language models. How much has been done there, and what is the direction? Okay, so there's a number of papers, but we were the first to do explanation for transformers, or at least among the first. I mean, we have a way of doing explanation for transformers that is has a proof, right? Let's say it like that. Okay. I think that applying this to language models would be a very good idea. And I think a lot of people are playing with that. But I think the real problem is, the thing that I would personally be interested in is, you know, we have all these language models that people are using now, wasting a lot of energy of this planet. And these language models, they are often answering nonsense, right? And the question is, you know, there's two questions. There's the question, why are they answering nonsense in this particular case? And maybe this can be improved. That's one question. But the other question is, what are actually the limits of these language models? And because I think no one knows them.
So I think that explainability and in particular the methods we have suggested and other people have suggested are a good handle to start looking at these. One of the problems, of course, that I have is that I don't have access to ChatGPT, the model, so that because it's behind walls.
And the same, I mean, maybe you can do it on a smaller scale, but then the question if you can answer, understand the explainability of the large models, if it's.
Well, I think what can I say? I mean, I think there has been a lot of talk about whether or not to regulate things. And I think people came to the conclusion that this is a good idea. But for this, and by the way, large language models is not the first time in the history of mankind that you regulate things, because in genetics, you have been doing this 20 years ago, right? So because people came to the conclusion that this was just not safe for this planet, to go about as companies everywhere in the world as they were. And so then they made rules, and there was actually a moratorium to that. And then, most people actually went with these rules. And that's probably the reason why our planet can still be, we can still live on that, right? So in a way, I think the one aspect of this was that at that time companies were saying, yeah, we can look at this ourselves, we can regulate, and we keep it safe, and by the way, just believe us, right? And I think that people came to the conclusion that it was important that other people that were not belonging to that company had the possibility to check up on things. And I think I think that insight from back in the day still holds, right? So, and so I think perhaps as a society we can say how we want AI to be, right? And we don't have to, agree. AI is not some divine thing that comes over us, right? So it's something that we can study, and we can regulate, and we can say how we want things, right? Perhaps I'm a bit optimistic, but I mean, why shouldn't I be? I mean, in the genetics field, this worked.
Okay, thank you.
Right. And perhaps those are some really nice closing words for today's seminar. Thank you very much, Professor Müller, for this really nice talk. Welcome back. Next scheduled seminar is in 2 weeks, on October 19th. We'll have Valentin de Bortoli from Google DeepMind giving a talk then. So thank you again for today.
Very nice. Thank you. Have a nice one. And next time I come.
Yes, very welcome.
Okay, then bye-bye.
Bye-bye.